Raymond Kui, 20. Raymond Kui, 20. Raymond Kui, 20. Aladdin Agana, 15. Aladdin Agana, 15. Aladdin Agana, 15. Noor Mohammed Birbidikov, 17. Noor Mohammed Birbidikov, 17. Noor Mohammed Birbidikov, 17. Mohammed Syed Dema, 34. Mohammed Syed Dema, 34. Mohammed Syed Dema, 34. Masudu Zaman, 5. Okay. Ibrahim Rob Job, 29.
Yes, Lord, I'm here.
Okay. Mohammed Temakir, 30. Okay. Mikhail M. Safa, 5.
Yes, Lord.
Okay. Solomon Carlton, 6. Hello?
Hello?
Solomon Carlton, 6. Solomon Carlton, 6. Solomon Carlton, 6. Sador Dadajonov, 8. Sador Dadajonov, 8. Sador Dadajonov, 8. Thermo Marik Daminov, 10.
Here.
Thermo, okay.
Yeah.
Priest David Gergov, 12.
Yes, Lord.
Priest,
Number
oh,
6.
you are number 6, Carlton.
Yeah.
Okay. Okay, Priest David Gergov, 12.
Yes, Lord.
Okay, okay. Hashibu Rahman Noor, 14.
Yes, Lord, I'm here.
Okay. Mehra Abu Hossein, 15.
Yes, Lord, I'm here.
Okay. Gentle Feeders, 21. Gentle Feeders, 21. Gentle Feeders, 21. Abraham K. Kromas, 22. Abraham K. Kromas, 22. Abraham K. Kromas, 22. B. Sir Phillips G. Russell, 25. B. Sir Phillips G. Russell, 25. B. Sir Phillips G. Russell, 25. Solomon K. Sawyer, 26.
Yes, Lord, I'm here.
Okay. Beckham Tirahan Mamo, 29.
Yes, Lord.
Okay. Next, Laikun Asifa, 30. Next, Laikun Asifa.
Yes, Lord. Yes, Lord.
Okay. Okay. Valery Botok, 31. Valery Botok, 31. Valery Botok, 31. Anna Akulova, 32. Anna Akulova, 32. Anna Akulova, 32.
Yes, 老师。
Huh? You are Abraham. You
Yeah.
are 22, right?
Yeah.
Okay. But I'm asking Anna Akulova, 32.
Oh, okay.
Anna Akulova, 32. Are you here? Anna Akulova, 32. Lawan Tobacco Grimarin, 33. Okay, I see. Big Noir Ikram, 34. Big Noir Ikram, 34. Big Noir Ikram, 34. Azamat Kalimulin, 36. Azamat Kalimulin, 36. Azamat Kalimulin, 36. Azamat Kalimulin, 36. Okay. Okay, so before before I move on to today's content, okay. So one thing I need to know is that okay, today is your fourth year in Nanjing University of Post and Telecommunication, right? So because of the COVID-19 pandemic, we have used online education for recent years. So have you taken any online exam in your previous semesters? Online exam in your previous.
Yes,
So which course you are taking the online exam?
previous all the exam we did it on the online.
All the exam. So you know the process
No.
about the online exam, right?
Yes.
Yeah. So because that I was just informed that okay. So this semester, okay, very possibly we still need to use the online exam to do the final. Okay. So if you know so you know that you need to prepare the two camera, right? So one is on your computer, okay, one is on your cell phone, okay, and yeah, so that we can watch you from the different angle. Okay, you know that process, right?
No, not like
No.
it was.
We just Laushi, we just using an app. That app have only one camera, like laptop camera, and Laushi watching us. That's all. But no use of two camera. I guess one camera is enough for looking after the student. What he doing.
Oh, so you just use one camera, no two camera, right? Because that for Chinese student, okay, if we use the online exam, okay, we ask them to okay use both the cameras from the computer and from laptop and from the cell phone, so that the teachers can watch them from the different angles. So in your previous semesters, you just use one camera, right? Okay, that's good. That will be convenient. That's good. That will be convenient. So you know that we will distribute the exam paper online, and then you need to write. You need to prepare.
Damn.
Huh? Hello. So you need to prepare some white papers and to write down your answer. And when the exam is end, okay, you need to take the photos of your answer sheet and okay, send your answer sheet to a certain email address. Okay. So in your previous semesters, so this is the process of your online exam. Is that correct? Is that correct? Hello?
Yes, sir.
Okay, so generally speaking, okay, so you just should know that okay. Anyway, so the final of this class will be also online. Okay, so let's say okay. So before we move to today's content, we need to say something about the homework one. Let me share my screen. Okay. Another question is that another thing is that for the final, okay, it might be some multiple choice and fill in the blanks, and also the short questions like that, or maybe some relatively complex questions. Okay, that are 4 types of questions in the exam. Anyway, so in homework one, okay, we have 6 questions. So let's say it one by one. Okay. So the first one, okay, the definition of the sorry, you can see the screen, right? Can you see the screen?
Yes, no.
Okay.
Yes,
So the definition of embedded system, okay. So firstly, if I ask this question, okay, you need to first answer me that it is a specialized computer system, and also, okay, it is application centered. So anyway, the embedded system is specialized. So it is a computer system, but specialized. Why it is specialized? Firstly, it is application centered because that each embedded system is specially designed for a certain purpose, which is applied for different area. So for different purpose, the architecture of the embedded system, okay, we have a different architecture of the embedded system for the different purpose. So it is a specialized computer system, so it is still computer technology based. But when comparing with the conventional computer system, embedded system have reducible hardware and software. It is because that it has strict requirements on function, reliability, cost, volume, and power assumption, as we discussed before, right? So the embedded system, it usually have limited hardware resource that the operating system and the software run must be reduced. So we cannot install a very large operating system or very complex software on it. Also, because the embedded system usually need to be low price. Okay. So how to be low price? Okay. We need to reduce the hardware and both the hardware and the software. But the reliability, not like our laptop or computer, okay, some of the embedded system have to run in some very harsh environment. So its reliability is very important. Also, its volume. Lot of embedded system has very small volume, which also causes that its hardware must be specially designed. Okay. So not like our conventional computer. Okay. Lot of embedded systems do not have much human interface modules, or we say the devices like the monitor or the keyboard, mouse, and so on. Okay, so this is about the definition of the embedded system. Then the second question, the features of the embedded system. So firstly, it is a microkernel. Okay. as I just mentioned, the embedded system usually have limited hardware resource. So not like the conventional operating system. The embedded system's kernel is small. For our conventional Linux system, its kernel, okay, the source code of the kernel, okay, usually can have a gigabyte size. Okay. But here for embedded Linux kernel, okay, for instance, it can have at least as 200 kilobyte size. Okay. Then specialty, okay, because that the embedded system is designed for a certain purpose. Okay, so that it does not need to provide the full functionalities. Okay, it just need to fulfill some certain functionality, and that's enough. So both the software and hardware can be reducible. Therefore, okay, the operating system should be specialized. Okay, the conventional operating system cannot be directly run on it. Okay, although okay, there are also Windows system and the Linux system. Okay, sounds like okay, conventional commercial system operating system run on it, but actually the Windows, okay, which running on the embedded system is the Windows CE, while the Linux system, okay, running on the embedded system is embedded Linux. So they are different, not the original conventional commercial operating system. Okay. Also, because that the hardware environment is different, okay. So the OS designed for embedded system is much different than our computer operating system. Then the development environment is also different. Okay. It's because that the embedded device usually cannot support the development by itself. So we have to develop the software run on embedded system on somewhere else. Okay, usually we develop the embedded system software, okay, on a conventional computer. Okay, then we move it to the embedded system. So we will call it the post-target development environment. Okay, we will discuss this one later. Then the typical architecture of embedded processor. Okay, so there are 5 such architectures. Okay, firstly, MCU. Okay, the which is also called the single chip computer. So it is very so this MCU, okay, appears very early in the history of the embedded processor. Okay. Then the NOR, let's see, 14 more. Wait a second. Oh, what's wrong? Anyway, the DSP, okay. DSP, this architecture is specially designed for handling the digital signatures. So it is optimized to run something like the FFT and with certain algorithm. Then MPU, okay. MPU is involved from the CPU, okay. So here in this class, okay, when we discuss the embedded processor, okay, we mostly mention about the MPU. Okay, for MPU, okay, the ARM MPU, okay, we know that takes a large portion of the MPU market. Okay. The SoC and SoPC, okay. So the SoC means the system on chip. Okay, so that it is so this one is some high-end embedded processor product, which means that we can integrate many things on a single chip. And also, okay, we can use SoC as a single unit when we try to construct an embedded product. While SOPC, okay, the difference between SoC and SOPC is that okay, SOPC supports the programming okay, on the chip so that we can extend the original functionality of the SoC okay, with the programming. Okay, usually we need to use the FPGA okay, to do the programming on the SOPC. Of course, that one is a little bit hard, okay, so we will not discuss that in this class. So generally speaking, there are 5 typical architectures of embedded processor. Okay. Then the difference between CISC and RISC. Okay. So the CISC is a complex instruction set computer. So the benefit of the CISC okay, is its instruction set contains many powerful instructions. But the disadvantage is that the instructions in the CISC instruction set have different lengths. As a result, it is inconvenient for the pipeline execution. Then RISC, RISC is the so-called reduced instruction set computer. When comparing with CISC, it has a limited simple instruction set. So its instruction set contains with the most frequently used instructions. It does not contain the complex instructions as the CISC. RISC also has its advantages and disadvantages. Its advantage is that, firstly, because the instructions in RISC instruction set, its length is fixed and the format are also fixed. So with the fixed instruction length and the format, it is suitable for the pipeline execution. Also, RISC has fewer addressing model, which also enhance the pipeline execution. Of course, because the instruction is short and simple, so for each instruction, its execution time is short. So all this makes the RISC optimized for the instruction pipeline execution. Of course, it also has disadvantages because that the instruction set is simple and less. So its instructions have comparatively less functionalities. To remedy this, okay, MPU, okay, like the ARM MPU, okay, is equipped with a large number of registers. So the typical RISC processors, okay, architectures include the ARM, MIPS, and so on. So this is a difference between the CISC and the RISC. So remember what is the pipeline, instruction pipeline, right? Okay, the so-called instruction pipeline is that we firstly divide the instruction into several components, for instance, 3 or 5, okay? Then, okay, then the pipeline can execute the instructions at the same time, okay, but with a different component. Okay, for instance, the fetching address, or we do some arranged execution or addressing. Okay, this for different stages. Okay, we can the processor can execute the instruction together. Okay, so the more stages, okay, the more instructions can be executed together. But with more stages, the architecture of the processor is more complex. Okay, and just speaking, we cannot say that although theoretically, the longer the pipeline, okay, the faster the execution speed of instructions. But because that there exists some jump, okay, jump or the branch instructions, okay. So the instructions are not always executed from the start to the end. So it may cause some problem for this instruction pipeline execution. Okay, this one we also have discussed in the class. Okay, then the hardware abstraction layer. Okay, the fifth question in the homework. So this one, okay, it consists three subcomponents. Okay, it is a layer of software abstraction between hardware and OS. Okay, so okay, it is you can imagine that it is an intermediate between the hardware and the OS layer. So it consists of the bootloader, board support package, and the device driver. Firstly, the bootloader. So this is a program that runs before the OS kernel. Okay, so it is like the BIOS in our computer. So here the program is hard-coded in a bootloader, like the BIOS. Okay. It is not in a RAM. Okay, it is hard-coded in a ROM. Okay. So what is the usage of the bootloader? Okay, this program. So it runs before the kernel. It actually prepare the needed running environment for the OS kernel. So firstly, okay, it completes the initialization of the hardware device. Then it establishes the mapping of the space, memory space. Okay. After then, it can load the OS, from the hard disk, of not all other hardware storage, load the OS into the main memory to run. Okay. If the mapping of the memory space have not been established, okay, then we cannot load any OS program into the memory to run. Okay. Then the board support package. So this one, BSP, okay, short for BSP, it abstracts the hardware operation for OS and made OS kernel independent of the hardware. So in general speaking, okay, the details about the hardware operation, okay, is supported by the BSP. Okay, then it support the BSP provide an interface to the OS to provide a general interface to the OS, so that when OS need to do some hardware operation, it just need to use the general interface, but do not need to consider the details of the device. So why the embedded system need the BSP? It's because that the embedded system, as we just discussed, it is a specialized computer system and application centered. So its architecture is different for different application purpose. as a result, not like our PC, okay, for our PC, okay, the architecture is very the most of our PC, okay, use the x86 architecture, okay. So that for this certain architecture, the OS don't have to use the BSP, okay, so that you can directly consider the x86 hardware operations, and that's okay. But for embedded OS, okay, it may not know, okay, exactly what is the architecture, okay, of the embedded hardware. Okay, so the BSP is needed. Of course, okay, the different OS have different definition of BSPs. Although, okay, the functionalities of the BSP are similar. Then the third component of the hardware abstraction layer is the device driver. So this one, okay, device driver, okay, this one works for both of the both our conventional computer and the embedded system. Okay, if we want to use a hardware, okay, we need to have its device driver. Okay, essentially, device driver, okay, is the program that directly operates and manages that hardware. So the device driver actually shared the details of the various hardware components and peripherals. So that the OS just use the interface, always the APIs of the device driver to use the hardware. The last question is the system service layer. So the system service layer, okay, it resides between the application layer and the OS layer. Okay. So essentially, system service layer is an interface provided by the system kernel for the application softwares. When an application software want to access OS services, it needs to go through the interface. This interface is usually called the system calls. So the system service layer, okay, it also includes several components. Firstly, user interface. For some of the operating system, okay, it provides the graphic user interface. Of course, if you want to use a graphic interface operating system in an embedded product, you need to make sure that it has the corresponding hardware that can support, okay, the GUI, okay, the graphic user interface. Well, for instance, suppose this embedded products do not have any monitor at all, so we cannot use the graphic user interface, right? Also, okay, if we cannot provide a graphic user interface, okay, maybe we can also provide something like the command interface and so on. Also, okay, this one we have for user interface, okay, it also includes the programming interface, okay, for the applications. Then task management, because that nowadays the operating system, most of the operating system are multitask, okay, so it supports multitask, and also because that they are multitasks running simultaneously, so we have the resource allocation problems and also different tasks may need to cooperate together. So how to cooperate together, okay, it also need to be done with the task management. The file system. So it makes clear the storage method and the data structure of the files on the storage device. So these three functionalities are also provided by the system service layer, okay, which can be accessed by the application level software through the interface. Okay, we say the system API or system calls. Okay, so this is the homework 1. Okay, so I have assigned the second homework, okay, 2 days before, okay. So be aware about deadline, okay. Let's move on to today's content. Okay, can you see my screen? Oh, it's not there.
Yes, Laoshi.
Yes, Lord.
Okay. Okay, so in last lecture, okay, we discussed the programming with ARM and C. Okay. So the first day, the programming with assembly, okay, is called the inline assembly. The inline assembly are different than the separate assembly file. Okay, although they have many similarities on the grammar and the syntax, but the usage still are different. Generally speaking, for the inline assembly, okay, these assemblies are as okay, either as a content of a C function. Okay, for instance, here, okay, this is the format of how to use the inline assembly. Okay. So we need to within a C function. Okay, so this enable IQ. Okay, so its functionality is enable the interrupt functionality. So it is still a C function. If we want to use this function, okay, we just use the normal function call, okay, and with the function normal function return. So this is different, okay, than the separate assembly file or separate assembly program. Okay, so within the body of the function, okay, if we want to use the inline assembly, okay, we need to use underscore, okay, this ASM, these keywords, okay, then use the 2 brackets, within the 2 brackets, this is the assembly code, okay. So why we need to use assembly, inline assembly in C, okay, so this is why we say that C can, C is somehow can have some functionalities like the low level programming language, like the assembly language or the machine language, okay. It is because that it has the inline assembly, okay, which can directly manipulates these registers, and So that here these 3 lines of assembly code, okay, it actually manipulates the CPSR, these registers, so as it actually change the control bits of the IQ, okay, and after we set these registers, okay, we actually enable the interrupt. Also, okay, we can disable the interrupt. Okay, you know the interrupt, right? Okay, if, for instance, if then as we just say about the system service layer, right? Okay, then when the application want to use OS service, okay, it need to call a system call, invoke a system call. So in this case, once a system call is invoked, okay, an interrupt will be issued, and then the control will be transferred from the application to the OS kernel. Okay. So this is the usage of the interrupt. But considering that, suppose here, okay, we disable the interrupt, then this control cannot be done. Okay, then the entire system will be broken. But then after in our last lecture, okay, we mainly discussed the separate ARM, okay, in other words, the mixed C and mixed programming with C and assembly. Okay. So firstly, we introduce some ARM instructions, okay, like the move, okay. So move is the basic instructions, okay, in ARM assembly. Okay, they have different usage. Okay, so for instance, here, okay, is simply copy the second the value of the second operand, okay, R1 here to the first operand, okay, R0. So this is execution result of these instructions. Then the second operand can be an immediate number, okay, like the here compound 64. This is the execution result of this instruction. There are also some variant of the move instructions, like the move T. Okay, so here is just set up. It just set the first, the highest 16 bits of the R1. Okay. Also, okay, this is MVN. Okay, this is a move not. Okay. So this is the move and its variant instructions. Okay, so this one, okay, it actually copies the not, okay, logical not, the value of the logical not of R1 to R0. Then we discussed something about how to use how to call a function, okay, from how to call a C function from the assembly program and vice versa, okay, or how to access a global variable. So this figure demonstrates how to access a C global variable from the assembly program. So here, this is not the inline assembly. Okay, this is init.s. This is a separate assembly program. Okay. So the global variable want to access is this one, global underscore var. To access it, we need to declare an import global underscore var. Then we can access this one. Okay. Like that load. Okay, this is load the value of this variable to a register R5. Okay, we have discussed that they have, generally speaking, there are 15 registers in an ARM NPU. Okay. Okay, please come back. let's continue. Then we discussed how to call a function that is implemented in an assembly program. So here, we say that this one, RNC underscore FUN, okay, fun. And from here to end, okay, this is these 4 lines of code is the body of the function RNC underscore function. So actually we can say that okay, this one is actually essentially okay, you see this one copy the global variable okay to the file okay, then it load okay the address okay. This one is the addressing okay, use the value within the R5 to addressing. Then here this line okay is add the value of R4 okay with 1. Then finally it store the R4 plus 1 okay, because now is this one after execution of this add R4 and compound 1 okay. This one R4 is value is increased by 1. Then it stores the value of R4 to the address of R5. Okay, actually the functionality of this INC FUN is to increase okay, the global underscore VR its value by 1. Okay. It's like that if we written in C, okay, it is somehow like the okay, we use a pointer okay, to store the address of this variable global VR underscore VR. Okay. Then we dereference the pointer and plus the value with 1. As a result, we actually increase the global underscore VR okay, with 1. Then how to use this function implemented in the assembly code? Okay, so firstly, we need to use the keyword export. Okay, now we say the pseudo instruction. Okay, is also okay. Okay, you can call it the keyword. That's okay. Anyway, okay, we need to declare okay the export RNC underscore function. After that, with this declaration, then in the within this main.c, okay, here this C code, we can call call the RNC underscore fun. So of course, when we call this INC underscore fun, we need to use the keyword extend because this one is not implemented within the main.c. Okay, this is implemented in an extend source code. So this one is not specialized for the function implemented in the assembly file. Okay, if this one in the C file, okay, you also need to use this extend okay, to call an extend function. Well, okay, the vice versa is how to call a C function okay, within the assembly program. So here, the function we want to call okay, is the main. Okay, of course, although main is the entry of a C program, okay, it is also a function. So, generally speaking, okay, when you run a C program, okay, actually it is the operating system who invokes the main function okay, in your source code. And here, okay, we assume that this assembly code want to directly access this main function. So the difference is that okay, we just need to use import okay to declare this main function. So we can say that, okay, either use an global variable in C program, or we want to use a function, okay, within the C program. We just need to use the import keywords to declare it. Actually, to some extent, we can also view this main. Although it's a function, we can still view it as a global variable, but it is just a global function variable. Okay. Then how to use this function in the assembly code? So here we directly use BL command to jump to it because this main takes no parameters. Okay. If here you know that for some main functions, okay, we need to provide some parameters. Okay. If so, okay, then we need to push something to the stack, then we do the jump. But here, because that the main is simply with no parameters, so we just use BL to jump to it. Okay, so this is the end of the last lecture, and we will move on to today's new content. For today, we start a new chapter, okay, the embedded Linux development. Firstly, let's discuss the development environment. Okay. So the embedded development is the so-called the host and the target development. So here the host target, okay, what is the host and what is the target? Where the host, okay, is short for the host machine. And the platform, okay, to edit and compile programs. So as we just mentioned, okay, the embedded system itself, okay, because it has a limited hardware resource and hardware process abilities, okay, so it cannot support the functionality to compile programs and to edit the programs. Okay, so here these things we will do in the host machine. Generally speaking, the host machine, the conventional computer, okay, such as x86 PC. Then the target machine, okay, target, okay, is the running environment of the developed program. Okay, so although the program is edited and compiled, okay, in the host machine, okay, its running environment is not there. Okay, it is the running environment is the target embedded system. Generally speaking, the target environment is a non-x86 architecture. The executable can run on the target. Of course, to achieve this goal, okay, when we compile the program on the host, we cannot use the conventional compiler. Okay, we need to use something called the cross compiler. So this figure demonstrates the host target development model. Okay. So on the left-hand side, okay, this is the host, and on the right-hand side, okay, this is the target. So on the host, it is usually run some conventional operating system. So here, the target is running some embedded operating system. So for instance, here we assume that this target environment, it is running the embedded Linux system. Then to develop the programs that can be run on the embedded Linux, okay, of course, we need to use some special compiler and such as, okay, the ARM Linux GCC. Okay. So of course, this kind of compiler and the development toolkits, okay, can only run in the Linux environment. So here in the host, okay, we can use something like the Ubuntu OS. But here Ubuntu OS, okay, can only run on the conventional, okay, computers. Okay, it is not an embedded operating system. Okay, this Ubuntu OS cannot run on the embedded products. Okay, this is different. The embedded Linux, okay, when comparing with the Ubuntu OS, they are different. So this one is very small, okay, but this one is really big. Okay. So we can see that there are some cross compiler, cross linker, cross debugger, and so on. Okay. All these things we is a toolkits for the cross development. So if this one is an ARM architecture, okay, suppose it is ARM architecture, then we can use the ARM Linux GCC toolkits for the development. Okay. In this class, okay, we will use the ARM Linux GCC toolkits as an example to demonstrate the embedded development. Of course, if for the different architectures, we may need to use different across development toolkits. Okay, so here we just assume that okay, the target environment is the ARM architecture, okay, and running the embedded Linux. So here we can use the ARM Linux GCC toolkits. If the running environment is different, okay, we need to consider we may need to consider different development toolkits. So we can say that for the cross development, okay, in this host target development model, okay, we need to somehow okay connect the host machine and the target machine. Okay. Can anybody answer me this question? If we want to connect something okay to our computer, can you tell me some method to connect something to our computer or to our laptop? Can anybody answer me this question? To use which method?
Do you mean physically or using internet?
Physically, let's say firstly physically.
USB?
Yeah, USB.
Yeah.
Anybody anything else? Physically connection. Beside of USB port, any other connection? Actually, well, I'm not sure that what do you mean by RJ stand for what? Okay, so how about non-physical connection? Non-physical connection. You know that with USB, okay, we use a USB wire, right? And connect them together. And how about non-physical connection? Ports, okay, use ports, okay, yeah, that's okay, okay. You can use ports, right? Okay, also we can use the Ethernet, right? Okay. So in general speaking, okay, we can use the serial ports, okay. We can use the Ethernet. Also, we can use the USB port. Different for communication between host and target. So why we need to connect them together? Okay. It is because that firstly, after we have finished the development on our host, because that we need to run it on the target machine, right? So we have to use some way to move the executable to the target. So here, either through Ethernet or through ports or use USB wire, anyway. So we need to move this executable to the target. Also, some debug, remote debug is available, for the toolkits. But for the remote debug, because why we need a remote debug? It is because that the target machine, may do not have the functionality to display the debugging information. It is very possible that the target machine, the target environment is simply a board, development board. But it do not have any monitor or something else. So its information can only be displayed in our host machine. So in this way, we also need to have the connection between the between the environment, target environment and the host environment. So for the debugging purpose or the simulator purpose, we usually use the serial ports for the connection between them. Of course, the Ethernet is also another kind of connection. So for the serial ports, the host uses some tools like the commit and minicon, to send a file to a target through serial ports, and also we can debug the executables remotely through other ports. Of course, we will discuss how to set the ports for the debugging purpose later. The Ethernet interface, so this refers to the network transmission. So this one relies on the TFTP, trivial file transport protocol. The USB port, this one is you know, right? In general speaking, this is about the software development environment for the embedded system, and this is the components during the development. So firstly, if we want to write a program or we want to launch a project, anyway, so we need to first have a design for this project. Then we need to have the IDE, obviously of course, within IDE, of course, we need to have an editor. Then we have a project manager, then a compiler and assembler. So the compiler is to compile the source code into the assembly code. Then the assembler will assemble the assembly code into the bytecode. The debug will link the bytecode with the libraries. Then finally the linker will transfer them into the executables. So you know the libraries, right? For instance, if you use the C to write some program, then many functions actually reside in some C libraries. So if you use the functions within the libraries, then during the compilation process, the libr here will link that library. And in more detail, actually it links the bytecode of the library to your program's bytecode, so that your program's function can be used. Otherwise, you actually just invoke the function, but your program itself do not have the executable code of that function. That code is within the library. So this is functionality of the lib. So this is the things that we have done on the host. Okay. Then we may have the debugger. Okay, remote debugger. Okay, then we use serials Ethernet USB parallel these ports. Okay, to connect to the target. Okay, and we start the remote debugging. Okay. Also, we can use some simulator to test our program. Finally, after debugging and the simulator, okay, then we can transfer the executable to a target board. Okay. For some complex embedded products, okay, we can just download the executable to it. But for some simple embedded system, okay, like the development board, you can just burn the code to it. Okay, we can also do not have the something like the hardware. Okay, they just have some it just have some simple storage. Okay? We can only burn the code on the board so that the program can be run on the development board. So here, compiler and assembler. As I just mentioned, the compiler it actually converts your source code, okay, to assembly code. Okay. So if it is be transferred to the assembly code, then we have the assembler, okay, that converts the assembly code to the binaries. So this one is called the .o file, is the object file. So when you write some program, okay, in your IDE, okay, and do a compilation, okay, use C++, okay, and do some compilation, you will see, okay, some object file are produced, okay, during the compilation process. So here, let's take a look at the object file. So each object file, okay, is independently addressed, okay. So what does that mean? Okay, what is independently addressed? So the first instruction of each object file is stored at the same logical address. Yeah. So here, when we say the address here, we always just mean the logical address because that the storage is not on the host. Okay, the storage is on the target embedded system, so that it can only use the logical address, okay, to store things. So the structure of object file is like that. For the low address, okay, it is the text section, okay, obviously the code. At the higher address, it will store the data used for the code. So the text, we say code, okay. Well, this one, okay, the code is executable. We know that, right? Because it stores the related instructions. So the instructions within this section are executable, and they are read-only. Of course, in the code section is read-only. So yeah, you know, you have learned the operating system course, and you should know that it somehow it like the it is like the structure of a processor. Okay, so this one is the code section. Okay, you know that one processor, okay, it have several sections, right? Okay, anybody tell me that one processor have several sections, right? Which how many sections one process have? one process has how many sections? Because that when executable is running, okay, it is actually will be created by the OS as a processor. Okay, so it actually also has so many sections. Anyone tells me, okay, how many sections one process has? No, I think that you should have learned what is a process, okay, in your operating system class, right? Or we say, or maybe it use another term we call a segment. Okay, the text segment, the data segment, within a process. You do not have learned them. Yeah, right. 6 or 5 segments, okay, within a process. Okay, it depends on. Yeah, maybe because of the different term. Okay, sometimes it called the segment. Sometimes okay, it calls the okay, the sections. Okay. So here, okay, actually it refers to the text section and a text segment and a data segment. Also, in some textbooks, okay, here the data segment is also divided okay, into dot data segment and dot BSS segment. Okay. So here the dot data segment okay, refers to the segment that okay, stores the initialized global and static variables. Okay. So for them, okay, it is read and writable. Okay. While .bss, okay, this segment stores the non-initialized global variables and static variables. So the so-called static variables, okay, is the variables, okay, starts with the keyword static, okay. So its usage is slightly different from the global, but it can be actually static variable can be its existence okay actually is it exists within the global scope. Okay. So here is a little bit hard to describe the difference between a static variable and a global variable within a few words. But generally speaking, you can consider the usage is likely is somehow similar to the global variables. So the global variable and the static variables they are put together. Initialized ones are here and non-initialized them are here. Okay. Then a linker, okay. So we just talk about the compiler and assembler, okay. So in some cases, okay, the compiler and assembler, okay, these two are combined together to be a single compiler. So that it will convert the source code directly to the bytecode. So it do not need to convert the code to the assembly code first, then transfer the assembly code to the bytecode. Okay, it directly transfer the source code to the machine code. The linker here, okay, but the linker is the same. Okay, the linker is need to address the object files and also the library files. Generally speaking, almost all the programs need a linker, okay, because of the functions we use are involved in different libraries, okay. So how to address them? Okay, this is the functionality of the linker. The linker generates a complete unified address image. So an absolute address image, okay, is usually generated in the embedded system, okay, especially okay in a system which is equipped with a memory management unit. Okay, each task can be assigned an address space separately. So you know that each task here is actually we can consider it as a process, and we know that for the process space, right? Okay, each process space are different, and when within operating system, okay, that use the virtual memory. Okay, you know virtual memory, right? Okay, so it actually each process space, okay, it can use all the virtual memory, okay. So the linker actually links the different object files together, and with here you just use link the different object files, okay. Of course, if there exists some libraries, it have similar, it is similar. So how to link them? Okay, we know that okay, the first action okay is text, okay, text segment. So it's the code. Well, okay, here this is initialized global variables and static variables. And here these three things there. This one is the last segment. Okay, it stores the non-initialized globals and the static variables. Okay. So how to combine them together into one single object file? Okay. So the text, okay. So actually the instructions, okay, they are put together. Okay. Then the initialized globals and the static variables, okay, they are put together. While the non-initialized globals and static variables, they are put together. Okay. So the merged, okay, the merged object file, okay, we can say that okay, they have the similar architectures or structures like the object file, okay. But during this merging, okay, we know that it's very possible that we have some branch instructions, okay, when we do the programming, okay. So and also okay, we may need to access some variables through memory address, okay. Then all this address need to be adjusted, okay, according to the relative position, okay, to we say relative address within this merged, okay, within this merged file, okay. So all this address will be adjusted, okay, by the linker. Okay. Actually, this is the main task of the linker. Okay. So here, suppose there is a library, okay, the library's code, okay, instruction will be also put here, okay, and also its data are put here. Okay. So this one can be replaced by a library, and it is the same. Okay. So this is the usage of the linker, okay. How to merge the several different object file, okay, into one single object file. So here, okay, this one is an example of the target and the target environment for in the embedded development. Okay, so this is ARM development board. Okay, in more detail. Okay, this is a friendly ARM. You can see that this is a friendly ARM, and you may notice that okay here on the right hand side. Okay, this is the keyboard. Okay, keyboard. Okay, so here. Remember that when we discuss the ARM, okay, we say that the ARM company, okay, it is its business model, okay, is chipless, and ARM itself just design the IP core, right? And it sells the design of the IP core to its partners. Okay, then the partners will design the rest interface module and combine them together. Okay, into an embedded product. So here the core board, this core board, okay, is designed by ARM itself, while other interface and peripherals, okay, are designed by the ARM's partner. Okay, so this, okay, the core board refers to the IP core. Okay, other interfaces and peripherals, okay, are designed by ARM's partner. Okay, so we can say that okay, suppose this board okay is our target environment. Okay, of course, we cannot have there's no monitor, okay, or other display, okay, or other display. If we want to know something about this board, okay, which program running on it, okay, we have to connect this board to our host and display the information on the host. Okay, so this is this one is our host environment. So we need to connect them together and do the cross compilation. And also, okay, when we want to run something on it, okay, and the running result also need to be displayed in this computer. Okay. So in general speaking, okay, because the development environment and the target environment they are different. Okay, so such separation okay makes the development make the embedded development much more complicated than our conventional programming. So the cross compilation okay, creates convenient conditions for different platforms of software transplantation. In general speaking, nowadays there are two typical implementations of cross compilation. The firstly is the Java mode. We know that JVM, right? Okay, the Java bytecode okay can be run on JVM. So that if we want to run the Java program in different platform, okay, we can simply install JVM on the target environment, and then we can run the Java program. Then another type of implementation is the GNU GCC mode. Okay, so this is the cross like ARM Linux GCC. Okay. So we develop the program in the host environment and move the executable to the target. So in this class, we mainly focus on the second implementation mode. Okay. Because that for some of the embedded product, okay, it cannot run JVM on it. So the embedded cross-compilation environment okay, is to build an environment on PC, but to programs that for embedded environments. There are two main features. Firstly, the cross-compilation environment is built on PC, but it coexists with the PC's compilation environment. So the IDE, okay, this cross development IDE is running on PC. Okay. but the executable, okay, the second feature is executable generated by the cross compilation, okay, can only run on the embedded target environment. So for instance, on PC, okay, we know that we use GCC, okay, to compile a C program, okay, as text 01, okay. Then okay, we run the test 01, and then that's okay. But here, suppose we compile a program that to be run on a embedded development board, okay, the ARM, okay, to be run on an ARM development board, okay. Then we use ARM Linux GCC, this cross compiler, okay, to compile it as the executable is text02, okay. Then here, suppose we run the text02 on PC, we will have a error, okay, because that the PC's environment, okay, it is usually the x86, okay, it cannot run, okay, a program that is of the ARM architecture. Okay. They have a different instruction set, so they can this one test02 cannot be run on the x86 PC. So why? Okay, if you are interested, okay, you can see the difference. Okay, how to see the difference? Firstly, okay, we can use the obj dump. Okay, obj dump is a command in Linux that can show the machine code, okay, of an executable. Okay, so we can see that they have different code between the text01 and the text02. And why? Okay, because that the instruction set is different. So the common used cross compilation toolkits, okay, including the cross, okay, and also the ARM Linux GCC. Here we meaning in this class, okay, we mainly use the ARM Linux GCC, okay, as the example. Okay. So this one can be done. This can be free, and there's no fee for it. Okay, you can download it freely. Of course, no. So now the highest version of Linux GCC is not 4.3.2. Okay, it have some higher version. Okay, so after download this zip file, okay, and just unzip the toolkits to the /user /local /arm /4.3.2. Okay. Then we need to anchor the .bash RC, okay, so as to provide an you know that this one is called the environment path. Okay, the environment variable path. Okay, so after that, okay, we can directly execute the executables within this directory. Okay, so this is this is the content of the this is the executables of the ARM Linux GCC toolkits. Okay, they have many components here, including GCC, G++, and so on. Okay, so it has the GNU being utils, okay, including a linker and assembler, and also the GCC. Okay, this one provides a C compiler. Okay, but nowadays these toolkits can also support some other programming language. Okay. Then glibc, okay, this one defines system calls and other basic function calls. So this is how to build the GCC cross compiler. Okay, so we first download it and firstly configure and compile the bin utils. Okay, so that we can get the assembler and linker. Then we configure and compile GCC to generate the GCC compiler. Firstly, if it is a higher version GCC toolkits, okay, so that we need to first build a C compiler, then build other languages compiler. then we configure and compile glibc to get the C libraries. Finally, we can configure and compile GCC to generate other compilers for other languages. Okay. Time is up. Okay, we stop here today. See you next time. So this Friday, okay, we still have a class. Okay. Okay, bye bye.
Okay, bye.